Greetings everyone, my name is Seantan. I am excited to present our paper, Efficient Graphics Representation with Differentiable Indirection. This is a work in collaboration with Karl Marshall, Derek Norozarai, Zhao Dong, and Zhenchen Li. Let us start with what differentiable indirection is. So differentiable indirection is very much like pointer indirection, where we query a location using an index or an address, which stores the address to the next location, which contains the final output. However, in our case, we learned these pointer values using gradient descent. Next, we look at why one should be excited to use differentiable indirection. The first reason is efficiency. Compared to multilayered perceptrons, our technique is order of magnitude more compute efficient, and compared to feature grid representation, we are order of magnitude more space efficient. Another reason to use differentiable indirection is its flexibility. We may use the technique in a variety of applications such as sign distance field representations, texture compression, texture filtering, complex BRDFs, and for compressing radiance fields. Not only that, but our technique is also very generic and potentially extends to applications beyond graphics. Finally, our technique exhibits properties of adaptive spatial resolution using a single indirection. In contrast, tree-based representations such as an octree or a KD tree require several levels of indirection to produce good quality results. This translates to our representation being more memory coherent compared to tree-based representations. So to summarize, our technique is adaptive, efficient, and flexible with wide variety of applications in graphics and potentially beyond. Next, we look at the technical details of differentiable indirection. At minimum, our technique requires two arrays. We call the first array storing the pointers as primary, and the second array storing the output values as cascaded. In the forward pass, we first query the primary array with an input coordinate x, and fetch the cells bounding the query location. We pass the cell values through a constraining nonlinearity f. The purpose of the nonlinearity is to bound the output values between 0 and 1 such that it points to valid memory location in the cascaded array. At this juncture, we note that the constraining nonlinearity can be baked directly into the array cells during inference for additional efficiency. Since the output of the array cells are bounded, the baked-in values can be easily quantized for more efficiency. Both these optimizations are extensively used in our applications. And finally, we interpolate the adjacent cells to obtain the pointer value y. Although we use linear interpolants, we note that any higher order interpolant may be suitable in this context as long as the interpolant is differentiable. Next, we use the pointer y to query the cascaded array. We again fetch the cells bounding the query location and interpolate the values to obtain the final output. For the backward pass, we compare the output with respect to the target and compute a loss which we then use for backpropagation through the array. We compute the gradient of the loss with respect to the output, and at the first node we multiply the incoming gradient with another gradient with respect to the array cell content. This updates the cells in the cascaded array. Note that computing this gradient is not unique to our technique. In fact, several prior work rely on this gradient to learn feature grid representations. However, our technique uses a second set of gradient with respect to the input coordinate or the pointer value y. This gradient is used for backpropagation and for updating the primary array. At the second node, we follow a similar recipe. We multiply the incoming gradient with the gradient of the array cells. Finally, the other gradient with respect to the input coordinates can be used for multi-level indirection if desired. With this, we conclude the technical summary of differentiable indirection. Next, we look at an intuitive explanation of differentiable indirection. We illustrate this in a 1D setting using a simple 1D array. We begin by representing the array content as a histogram. To obtain continuous output, we interpolate the adjacent cells in the array as shown. Next, we visualize the two gradients that we compute at each node during backpropagation. The first gradient with respect to the array cell contents, and the second with respect to array input coordinates. The purpose of the first gradient is to update the array values, while the second gradient is used to learn pointer values in the primary array. On our histogram, we represent this gradient with respect to the cell values using vertical blue arrows as shown on left, while the gradient with respect to the input coordinate is shown in orange with horizontal arrows. Let us take a moment to analyze the two gradients. The gradient with respect to the cell content, indicated by blue arrow, adjusts the cell heights in the histogram. But the gradient with respect to the input coordinate y is trying to adjust the cell widths. Let's look more closely at the second gradient. On this slide, we highlight the intention to move the cell boundaries using the orange arrows. Let us also show a hypothetical array in red with variable cell boundaries. In such case, the gradient represented by the orange arrows should move the cell boundaries on the red array as shown. In practice, the information regarding the cell boundaries is stored as pointers in the primary array. The primary and the cascaded array combined represents the adaptive resolution as illustrated by the hypothetical red array. With this, we conclude our explanation regarding adaptive resolution in differentiable indirection. Next, we look at a few exemplary uses of differentiable indirection. Our technique is useful for compact SDF representations, where we use a simple network composed of a 3D primary and a 3D cascaded array. We can also use it for texture compression, where the network is composed of a 2D primary and a 4D cascaded array. We noticed from our experiments that a higher dimensional cascaded array yields better quality compression. With a small modification to our compression-only network, we can jointly treat both compression and filtering. This technique is useful for real-time rendering, where we no longer need to have separate hardware for both compression and filtering. In the context of shading, we can use our technique to represent isotropic GGX function. The function is used to model glossy surfaces. Similarly, we can also model a complex BRDF such as Disney using our technique, while also being more efficient to evaluate compared to reference implementations. And finally, we apply our technique to radiance field compression, where we compress regular grids storing density and view-dependent RGB using two sets of 3D indirections. Next, we discuss empirical evidence of efficiency based on an example. We illustrate the efficiency of our technique by approximating the isotropic GGX, which is a 2D function with a highly nonlinear scalar output. Since it is a 2D function, we visualize the function as a monochromatic texture containing HDR values. Such function is often used for shading glossy objects as shown on the right. In this context, we compare and approximate isotropic GGX using a variety of neural techniques such as multilayer perceptrons, a single-level interpolated lookup, a combination of a single-level lookup and an MLP, and finally differentiable indirection. For this task, differentiable indirection requires 1 kilobyte of parameter space, 36 flops of compute, and 16 bytes of memory transfer. Compared to ours, an MLP-only network requires 4 times more parameter space, 2 orders of magnitude more compute, and byte transfers. Whereas a single-level grid requires fewer compute and byte transfers, the benefits are outweighed by the enormous parameter space required by a single-level lookup. And finally, a combination of an MLP and lookup strikes a better balance across the three criteria, but overall our technique still performs better. Next, we illustrate the efficiency of our technique using a few more examples. For SDFs, we represent 12 GB worth of surface sample points in just 24 megabytes. Then for texture compression, our scheme can compress several times the raw size of an RGB texture. For real-time applications, we may also use it for joint texture compression and filtering using a single network. In the context of shading, we can efficiently approximate Disney BRDF by replacing 200 plus flops of compute with just a few lookups. And finally, differentiable indirection can be used to compress pre-trained radiance fields by orders of magnitude. The video collage shows differentiable indirection in action for a variety of applications. Thus, we end our presentation with the following conclusion. That is, differentiable indirection is an adaptive, highly efficient, and flexible neural primitive with various applications in graphics and potentially beyond. Thank you for listening to our presentation, and please check our website for more details and videos.